you very much, Enrico, and thanks again for the invitation to speak at this nice seminar series. This talk is going to be based on two papers that I wrote recently. The first one with Luca Della Cretas, who's in Chicago, and the second one more recently with Hanji Jiang, who's just finishing his PhD in Oxford. And I think I just saw him in the audience there. Yes, Hanji is here as well. Okay. The starting point is that if we have some generic interacting quantum field theory, what we expect is for it to thermalize. So let me be a bit more specific about what I mean by this word thermalization in this talk. So what I'm imagining is we start with our system already in some thermal state at temperature T, and then we're going to knock it out of equilibrium, for example, by injecting some energy here. And what we expect is if we wait a very long time, eventually the system is going to return to a state of thermal equilibrium. Okay, and the question that I'm interested in addressing is how does this process happen? So broadly, what we expect is we can divide things into two regimes. So at early enough times, we expect there's going to be some complicated microscopic dynamics controlling what's happening. But eventually, in a generic system, what we expect to happen is, first of all, it achieves a state of local thermal equilibrium. So it locally thermalizes. And once this has happened, we have very good effective theories that then describe the subsequent relaxation back to the final state of global equilibrium. And those are called theories of hydrodynamics. Okay, and so if we want to understand thermalization, I mean, a really key part of it is to understand how is it that this hydrodynamic description emerges from the microscopic dynamics of the field theory. And if we can understand how that happens, then we should be able to answer lots of questions about it. So for example, how long does it take for this local equilibrium to establish, i.e. what is the time scale here beyond which we can just let effective field theory take over? Second question would be, once this hydrodynamic theory emerges, right, our system behaves like some kind of fluid, what are its properties, right? How are the properties of this fluid related to the kind of microscopic couplings and particles and so on of the theory? Okay, and many other questions like this. I'm going to try and address this question today just by considering a simple observable, which is the thermal two-point function of the stress tensor in a field theory. Okay, so I probably don't need to tell the audience here. In general, answering these kind of questions are hard. So one reason is just practical difficulty, right? To study thermalization, we need to compute thermal correlators at real time. And that is just, practically, very difficult usually. There's also a more conceptual difficulty, right? Which is if we expect emergence, right? If we expect hydrodynamics to eventually come out, what that usually is going to involve is a big reorganization of the degrees of freedom at late times compared to those at early times, right? The excitations of a fluid, right, are usually quite different than the excitation, kind of particle-like excitations of a field theory. Okay, and so if we really want to see this whole transition happen, we need to study these correlators, right, over some big range of timescales, right, where we expect, big reorganization of the degrees of freedom. Okay, so what I want to talk about today is a certain kind of class of simple cases where things simplify enough that you can really make progress on these questions in a kind of pen and paper type way. So the type of theories I'm going to be talking about are 1+1 dimensional field theories in an infinite volume in the limit of high temperatures. Okay, so to understand why this is a nice limit where things simplify, let's start with the simplest kind of 1+1D theory, which is a 1+1D CFT. So what's very nice about 1+1D CFTs from this perspective is they get around the first problem of it being hard to compute correlators, because at least the two-point function of the stress tensor, even at finite temperature, we can just compute it explicitly in a 2D CFT. And furthermore, it's universal, so it doesn't depend on what the CFT is. So what I'm showing here is the retarded two-point function of the right-moving component of the stress tensor in the thermal state. Okay, and it has this specific form, so it's basically some derivatives of delta functions. So that's the nice thing about 2D CFTs. The bad thing, from my point of view, or from the point of view of this talk, is it's very boring. So, right, there's no kind of emergence of hydrodynamics in this formula, right? There's nothing interesting that happens at late times as compared to early times. What we have is just this two-point function, right, supported along the light cone, right, stress tensor propagates freely along the light cone at all times. Okay, and so what's happening is basically just in 2D, conformal symmetry is so constraining that it prevents this emergence of hydrodynamics from ever actually happening. So if we want a more kind of realistic model of thermalization, well, I would like a more realistic model. What I'm going to do to achieve that is to break conformal symmetry. So I'm going to start with my 2D CFT, and I'm going to deform it by some relevant scalar operator O with dimension delta. Okay, this operator has a coupling lambda, which is dimensionful, but in the thermal state, there's a natural dimensionless coupling, which is just made by absorbing enough powers of t into the coupling lambda, and that dimensionless coupling is what I'm going to call lambda bar. Okay, and in this talk, from now on, I'm going to focus on what I call the high temperature limit, which is simply the limit where this coupling is very small. Okay, so one way to think about this high temperature limit, perhaps a more kind of theoretical way of thinking about it, is what we're doing is we're breaking conformal symmetry, right, in the thermal state, but in a weak way. So physically, what that means is that since we've broken conformal symmetry, we still, we expect hydrodynamics to eventually emerge. Okay, we expect it to emerge slowly since it's a very weak breaking, but nevertheless, it should emerge. And from a practical point of view, right, the advantage of this high temperature limit is that we can preserve some of the nice theoretical control we have in the CFT. So in particular, we can hope to work perturbatively in this small coupling, lambda bar, right? That's what I'm going to call conformal perturbation theory, right? And access this hydrodynamic limit of the field theory. Okay, so that's basically the setup. I'm going to make a couple of assumptions on the CFT. So the first one is that the central charge C is large, infinitely large. And the second assumption is that the only conserved current in the CFT is the stress tensor. Okay, now some of what I'm going to say doesn't rely on either of these or only relies on one of them, but certainly I think the whole kind of body of what I'm going to say relies on both of them together. Okay, so that's the basic idea. Hopefully, it sounds kind of plausible that this is a useful setup and we're going to be able to make some progress here. What I haven't really explained yet is how we're going to get around the second problem that we expect, right? If some hydrodynamics emerges at late times, that's going to involve some reorganization of the degrees of freedom. So let me be a bit more specific about what that involves. So assuming hydrodynamics eventually comes out, this is an effective theory, and we can use it to just compute what should the stress tensor two-point function look like at very late times and very long distances. Okay, and that is the expression I've written here. So the important bit is the exponential, and in particular, this part here inside the exponential. So this is telling us that at late times, we expect a two-point function to be localized along the sound cone, i.e. along x equals CST, where CS is the speed of sound in the fluid that is eventually going to emerge. Okay, so this is just saying in a fluid, the excitations are sound waves and they travel at the speed of sound. Okay, they also decay in time, right? Their decay rate is controlled by the fluid's viscosity, which is this symbol here, divided by the energy density of the state plus its pressure. Okay, so this is what we expect the two-point function to look like at very late times, right? And what's challenging about this is it basically looks totally different to the CFT two-point function, which is what we expect at early times. Okay, and so what, really the problem is here is that if we really want to see hydrodynamics emerge, we're not going to get this two-point function from adding some small correction to the thermal CFT, right? We have this small parameter lambda bar, but what we're eventually going to have to do is resum this expansion in lambda bar to access the correct late time limit. Okay, so that's kind of, in general, that's sort of bad news. But this high temperature limit that I'm advocating, actually, things aren't so bad in that limit. And the reason is in the high temperature limit, the excitations of the fluid are actually not so different to the excitations of the thermal CFT. So in the thermal CFT, the stress tensor just propagates freely along the light cone. In the fluid, it propagates at the speed of sound. We can just compute the speed of sound perturbatively, right? And there's no issues with perturbation theory here. We can compute it, and in the high temperature limit, we get some small correction to the speed of light. Okay, so in other words, in the fluid, the sound waves, they don't travel quite at the speed of light, but they travel very close to the speed of light. And so what that means is if we want to see the emergence of hydrodynamics in this high temperature limit, okay, it's enough to just focus on what's happening near the light cone. Okay, at early times there, we should see the stress tensor propagating, and at late times, we should see this sound wave, which lives very close to the light cone. And hopefully we can see the interpolation between them. Okay, and so from the practical point of view of, okay, oh no, we're going to have to read some conformal perturbation theory. In practice, what I expect we're going to have to do is just resum it in a certain kinematic regime, which is near to the light cone. Okay, so that's sort of the basic motivation for what I'm going to talk about. And what I want to essentially explain to you is this limit, so the high temperature near light cone limit of the stress tensor thermal correlator. I want to argue basically that this is explicitly accessible, i.e. we can really compute exactly what it is. And furthermore, that it's universal. So that is, it doesn't actually depend on the CFT that we start off with. Okay. So once I've presented this expression for the two-point function, they can, from that, we can then deduce lots of interesting information about thermalization. So for example, we're going to be able to see that indeed there is a transition from kind of thermal CFT behavior at early times to hydrodynamics at late times, and the time scale, characterizing when this hydrodynamics emerges is parametrically long in this dimensionless coupling, which is kind of what we expected from weak symmetry breaking. I'm also going to show that there's a nice physical intuitive picture of how conformal perturbation theory breaks down, if we try and push it to very late times. Hydrodynamics should emerge, perturbation theory breaks down, and I want to explain there's a kind of simple picture of how that's happening. And similarly, if we take our late time theory, which is hydrodynamics, and try and push that to early times, there's going to be a nice physical picture of what's causing it to fail as the kind of assumption of local thermalization breaks down. And thirdly, from this two-point function, we can just read off explicit expressions for infinitely many of the fluid transport coefficients. So for example, the speed of sound, the viscosity, all these observables that characterize the fluid that emerges, from this two-point function, we can just read off exactly what their values are and how they're related to the microscopic theory. And what's, to me anyway, the most interesting thing about this is their values are universal, i.e. they don't depend on what the original CFT was. All they depend upon is the scaling dimension of this operator. Okay. So that's kind of the summary of results. I'm going to explain them in a different order than the order there. So let me tell you the kind of plan for how I'm going to go through things. So first of all, I want to argue for this expression for the high temperature near light cone limit of the stress tensor correlator. And to get there, what I'm going to start off doing is trying to do conformal perturbation theory in momentum space. I'm going to see that, naively trying to do this, I end up with, I'm going to see that it breaks down near the light cone. And then what I'm going to do is just propose a very naive way to resum this to give us something sensible near the light cone. Okay, so I'm not going to be able to prove to you that this is the correct thing to do. I'm just going to do the most naive resummation possible. And then we're going to explore the consequences of this. Okay, and once I've done that, I'm then going to give you a bit more reason why you should believe that this very naive resummation is the correct thing to do. So the first reason I'm going to try and give you to believe this is I'm going to look at holographic theories, okay, of this type. So in holographic theories, we can really compute exactly, various quantities related to thermalization in these types of field theories without any assumptions or resummations or anything like that. And what I want to show you, for example, we could compute the viscosity of the fluid. We can compute something called the butterfly velocity and various other things. And what I want to show you is if you compute these things in holographic theories, you get exactly the same answers as you get by doing this naive resummation. So this is sort of evidence, if you like, that at least in holographic theories, this is really the correct answer. Then after that, hopefully I'm going to have time for this. I want to go back and think not just about holographic theories, but more generally, what am I doing when I'm doing this resummation, What effects am I resumming, Or in other words, what are the effects that I need to carefully take into account to make sure I get the correct thermalization process? So I'm going to do that. I'm going to go back to conformal perturbation theory in real space. and I give you at least a kind of cartoon of what is the mechanism that's causing these theories to thermalize. Okay, so that's the plan. Are there any questions before I get going? Nope. Okay. So let's start off by trying to compute this two-point function in conformal perturbation theory. So the first thing to say is the emergence of hydrodynamics, just it turns out, looks much simpler in momentum space than in real space. So we're going to start off in momentum space. We're considering 1 plus 1D field theories, and there, the kinematics in 1 plus 1D are quite helpful to us. So in general, in 1 plus 1D, we have 3 components of the stress tensor, but really only 2 of them are independent. Okay, sorry, only one of them is independent. So we really only have one independent two-point function of the stress tensor. I'm going to take that to be the two-point function of the right-moving component, right? And I'm always going to be talking about retarded two-point functions, and I'm going to call that G of omega and K, right? And the other two-point functions of the stress tensor I can just get using the word identities coming from local conservation of the stress tensor. Okay, so this is going to help us a little bit. So in the CFT, right, we can easily compute what the stress tensor two-point function is. This is just the Fourier transform of what I had before, and it's given by this function here. Okay, and perhaps the most important thing about this is it has a pole at omega equals k, right? This is just saying, right, stress tensor propagates along the right light cone forever. Now, I'm not interested in the CFT, I'm really interested in this QFT that I get by deforming it. And the way I'm going to try and access this two-point function in the QFT is to do an expansion in powers of lambda bar squared, right? Conformal perturbation theory. And I'm going to try and compute, at least just for now, the first correction to the CFT result, which I'm going to call G2. Okay, the lambda term is 0, the first correction is the quadratic one. Okay, so what's nice about this first correction is we can really compute it exactly, and furthermore, it's universal, i.e. it doesn't depend on what the CFT actually is. So let me try and motivate for you why this particular correction is just universal. So to understand this, let's temporarily think about a different two-point function, which is the two-point function of the trace of the stress tensor. Okay, so in the CFT, this would be 0 up to contact terms. In the QFT, it's not 0, but it's related by a word identity to the two-point function of the scalar operator. Okay, and the important thing about this relation between these two things is there's a factor of lambda squared between them. And so what that means is if I want to compute the lambda squared correction to the trace two-point function, I only need to know the two-point function of the scalar in the CFT itself. Okay, the thermal two-point function in the CFT itself. Okay, and in 2D CFTs, okay, we know explicitly the two-point function of scalar operators, and they are universal, right? They only depend on the dimension of the operator and not on what the CFT actually is. Okay, so by this kind of chain of arguments, I can get an expression for the correction to the trace two-point function, and then using the conservation word identities, I can turn this into the lambda squared correction to the right-moving stress tensor two-point function. Okay, and if I do this carefully, right, turning these twiddles into equal signs, what I find is the correction to the right-moving two-point function looks like this thing here. Okay, and it's this term here on the last line proportional to the scalar CFT two-point function that's really the important one, right? That's the one from this argument above.
Sorry, can I ask very stupidly, like the lambda dependence in the right-hand side, is it inside GCFT00 or?
So in this expression here, GOO is some function of lambda, and we have no idea what it is. And what we're doing here is we're expanding, we want to expand this thing out at small lambda, which means we just want the kind of the conformal limit of this guy here.
No, it's more naive than this. Like in the last expression, is it still there or did it drop?
Sorry. So G2, let me rewind. So there's a lambda squared multiplying this correction. Sorry. Yeah.
Thank you.
Yeah. Okay, so this is the first correction. And motivated by what I said before, what we want to do is look at this thing near the light cone, i.e. as omega goes to k. And what you can see here, well, first of all, we need to examine what does this thing look like near the light cone. Okay, as I said, this is known explicitly. It's just given by this kind of complicated looking combination of gamma functions. Okay, and for now, the only important thing about this two-point function is on the light cone, i.e. at omega equals to k, this just goes to some finite, function of k. Okay, so in the vacuum, right, on the light cone, this correlator would probably have some weird non-analyticity in it. But the point is, in the thermal state, thermal excitations decay, right? And there's nothing interesting happening on the light cone anymore. It's just some, right? It's just some complicated looking, but function of k, but there's nothing special about it. Okay. And what that means is when we take the omega goes to k limit of the full correction, we're going to get from here, so we're going to get a divergence. This thing goes like 1 over omega minus k squared, and we're going to get a 1 over omega minus k squared term from here. Okay, so this is what the correction looks like, the leading term near the light cone.
Can I ask a very, very quick question? Like the conformal dimension delta equal to 1, is it physically special or it just needs like some kind of regularization? Because in the previous expression, for example, you have a pole. I was wondering if it needs some care
It's a
or
good
not.
question. Yes, it needs some care. And the reason it needs some care is when I write down this ward identity, for the special case of delta equals to 1, there's some extra kind of anomalies that people call matter anomalies on the right-hand side, which I have not taken into account. So I think, let me say, I think the same procedure would work. The answer might be slightly different at these intermediate steps. But eventually, when I get to the final answer I'm going to present, if you just send delta equals to 1, everything is totally smooth. So I think, yeah, some of these intermediate steps, it looks like delta goes to 1. Things are singular, but they're not. Yeah.
Thanks.
Okay, but thank you. That's a good question. Yeah. So this is the correction near the light cone. And now I can compare this to the CFT result near the light cone, which is basically 1 divided by omega minus k. And what you can see here is that the first correction in conformal perturbation theory near the light cone is more singular than the first term. Okay, and this is a kind of, this is the smoking gun or a hint or whatever you want to say that near the light cone, conformal perturbation theory is going to break down. Right, this term becomes much bigger than that term. Okay, and so if we want to get a sensible understanding, right, and that's what we expect, right? That's where we expect this emergence of hydrodynamics to happen. So this is right. It looks bad, but it's physically sensible. And so what we want to do, or what we need to do if we want to really understand what's happening near the light cone, is find a way to deal with this divergence. And so the proposal here is just to do the most naive thing that you can imagine doing, is just take this correction and resum it into the denominator of this, right? So that we get two-point function, which looks like this thing here. Okay. Now, of course, based on what I've presented, this is not really justified, right? I haven't presented what happens at higher orders, and I don't know, right? We're not able to do the calculations yet. So what we're really doing by making this resummation is that, for this to be correct, what it means is that at higher orders in conformal perturbation theory, right, each power of lambda bar squared must get more and more divergent near the light cone, such that it can be resummed into this. And furthermore, right, the coefficient of these, getting worse and worse divergences is just given by powers of this same universal function. Okay, so for now, you can just take this as this is just a very naive guess of what is the correct thing to do. And we're going to work with this guess. And so the conjecture is that this guess is the correct answer. Okay, there's a leading order expression in the high temperature near light cone limit. That is if we took the full correlator and took omega minus k to be small, and lambda bar squared to be small, and them to be the same order of magnitude. Okay, this naive resummation gives you the correct answer. Okay. So, another way of saying the same thing here is that this proposal is basically saying the weak breaking of conformal symmetry, how does it affect the two-point function near the light cone? What it does is it takes the CFT two-point function, right, which would be this thing here without the last term there, okay, and just generates a small self-energy term, okay, for this CFT mode, right, which would otherwise just propagate freely. Okay, and if I go back and put in all the correct factors and get rid of the twiddles and make them equal signs, what I find is this self-energy, sigma of k, is given by this function here. Okay, so it's related just to the universal two-point function of the scalar in the thermal state. Okay, and I know exactly what that is. So if I substitute that in here and simplify things a little bit, I find that the self-energy I'm generating by breaking conformal symmetry is given by this function here. Okay, so that's the proposal, and that's basically what I'm going to assume for the next few minutes. So the function here, it looks complicated, right? It's a bunch of gamma functions and so on, but there's one very simple thing about it, which is it doesn't depend on what the CFT actually is, right? All it depends on is this dimension delta. Okay, and this is like, totally different than what you would expect in higher dimensions, right? Where, how does a CFT thermalize? Well, depends on what the CFT is. Okay, so this is a proposal. Now what I want to do is just spend a few minutes examining this, right? Some of the consequences, right? If this is really the two-point function, right, what does that tell us about the properties of how thermalization happens? Okay, so the first thing to notice about this is, okay, we've generated a self-energy for our excitation here, but we still have a factor of k here, and what that means is, although we've generated a self-energy, right, this mode is still gapless. Okay. And okay, and this is what its dispersion relation is. How do we interpret this? Well, to interpret it, the first thing we can do is, first of all, let's look at this mode at small wave numbers. Okay, so we're near the light cone. Small wave numbers basically means we're looking at late times and long distances close to the light cone. Right, so this is the hydrodynamic limit, right? This is where we expect the effective theory of hydrodynamics to have taken over. So we can just take this and expand it out at small k. And if hydrodynamics has really emerged, what we expect is to see the dispersion relation of a dissipative sound wave, right? Which is what the hydrodynamic two-point function has near the light cone. Okay, so hydrodynamic tells us what the dispersion relation of a dissipative sound wave looks like. So leading, linear order in k, there should be some real term here where the coefficient tells us the speed of sound. A quadratic order, we should have a negative imaginary term whose coefficient tells us the viscosity of the fluid, okay, and so on and so forth. There's just an infinite series expansion here, which is just the derivative expansion of hydrodynamics. Okay, and indeed, if we expand out this explicit self-energy, what we find is something that has exactly the right form to be the dissipative sound wave of hydrodynamics. And so essentially, what this resummation is doing is generating this self-energy, which is turning, our freely propagating thermal CFT mode into the hydrodynamic sound wave. Okay, so when omega minus k is much bigger than this thing behaves like the thermal CFT. When it's not, it behaves differently, and indeed it behaves like hydrodynamics. Okay, and since we have an explicit formula for this sigma, we can literally expand it out, look at the coefficients, and read off what is the speed of sound in the fluid, what is its viscosity, etc., etc., etc. Okay, so let me present what we get if we do that. So the speed of sound we get by expanding this out is given by, in the high, in the high temperature limit, or always in the high temperature limit, is given by this function here. Okay, now the speed of sound is something we can reliably compute just with equilibrium conformal perturbation theory, and we get exactly this answer. Okay, so if you like, this is a kind of consistency check that this resummation I'm proposing, right, at least reproduces the correct speed of sound. And next order in expansion, we can read off the viscosity in the high temperature limit, so it's given by this function. Okay. Now, we don't know in general what the viscosity should be, but we know it better be positive. Okay, and so a consistency check is to take this complicated looking formula and check, is this always positive for delta lying between 0 and 2? And indeed, it is always positive, right? So again, this is a kind of consistency check that we're not doing something that's obviously wrong. And we can keep going to higher and higher orders in this derivative expansion and read off all these hydrodynamic properties of the fluid. Okay, now again, the explicit expressions perhaps aren't particularly illuminating, but what's very nice about these, and I keep emphasizing this because it really is amazing to me, is they're universal, right? All you need to know is the dimension of delta, and that will tell you all the properties of the fluid that emerges. And this is very, very different to the usual situation where, what is the viscosity of, the QCD plasma? Well, it depends on exactly what the Lagrangian of QCD is, right? Here, things are almost completely independent of the microscopics. Okay, so this is the kind of the hydrodynamic limit of this result and what it tells us about the fluid that emerges. Now I want to look at a different aspect of this resum 2-point function, which is a bit more subtle, but important, and also tells us something very interesting about thermalization. So that is that this self-energy apparently has poles at some isolated imaginary values of the wave numbers, right? In particular, at these wave numbers here, where n is some non-negative integer, our self-energy has poles. So let me rewind a second. Here's the self-energy. It's got some gamma functions here. And this second gamma function, the numerator, has poles, okay, as when the argument is equal to 0 or negative integers. Okay, so what does that mean? Well, what it's really telling us, right, is not that really the exact 2-point function self-energy has a pole there, but it's really just telling us that our high temperature near-lightcone expansion is breaking down right near these isolated imaginary values of the wave number. Right, so if I go back, our assumption is basically, the omega minus k term is the same order of magnitude as the self-energy. And what you can see is, right, when I'm near pole, when I'm close to a pole of sigma, right, this term is going to blow up and be much bigger than that term. And so our approximation is just breaking down. Okay, and so the conjecture is this is the correct answer at high temperatures and near the light cone, apart from these special imaginary values of k, right, where something more complicated is happening. Okay, and we know what the more complicated thing that is happening there is. There's a very nice physical picture of what's happening there and why things are breaking down. So to understand what that is, we need to go back and think about, well, let's start off by going back and thinking about thermal 2-point functions in the CFT itself. So in particular, sorry to keep rewinding backwards and forwards here, let's go back to looking at the thermal 2-point function of the scalar in the CFT. Okay, this thing has poles, where the gamma function has poles, these two gamma functions. Okay, so the first one is going to give us kind of right-moving modes, and the second one is going to give us left-moving modes, right? And these modes are the excitations of the scalar in the thermal state of the CFT. And what's going to be important are the left-moving modes. Okay, so they have dispersion relations in the CFT, which are just given by this expression here, where n again is 0, 1, 2, 3, etc. So that's in the CFT. When we break conformal symmetry, two things are going to happen. The first thing is we're going to get some corrections to this, which presumably will be small, and they're not very important. The second thing, which is much more important, is that when we break conformal symmetry, the 2-point function of O mixes with the 2-point function of the stress tensor. And what that means is these excitations of the scalar operator will turn into poles of the stress tensor 2-point function as well. And what's happening at these special imaginary values of the wave number is these excitations are crossing the light cone. And so, yeah, this is, all these words is perhaps a bit too hard to absorb. So let me draw a picture that hopefully makes this a bit more clear. So what I'm plotting here is the spectrum, right? Let's say the dispersion relations of the poles of the stress tensor 2-point function. for imaginary wave numbers. Okay, and that means the energies are also going to be imaginary. So in blue here, this is this right-moving mode we've mostly focused on, which is just the CFT mode plus some self-energy. So it moves kind of approximately along the light cone like this. Okay, a small k, this is what we interpret as the hydrodynamic sound mode. And in orange, okay, I'm showing these left-moving excitations of the thermal excitations of the scalar. Right? These are left-moving, so they move upwards in this diagram rather than down. And what you can see is that special imaginary values of k, right? This excitation also, comes very, very close to the light cone, right? And then at some higher value of k, this excitation comes very, very close to the light cone. Okay, and so what's happening is our result is breaking down near these special points because we've got some extra degrees of freedom near the light cone, right, which this resummation is not taking account of properly. Okay, and so what happens exactly at this point here and exactly at that point there, I don't know. What I expect is once we properly account for these, extra degrees of freedom, that these apparent poles in the self-energy will get resolved into branch points. There'll be some branch point here where these poles kind of do something complicated, but then coming out of it, we just have this one here and this one here again. And the same here. Something complicated happens, and this one comes out, and this one comes out. Okay. So you might wonder, why am I going on so much about some, weird singularity, some imaginary value of k, right? If I just look at real k, everything's going to look normal, and who cares about this? The point is that these, singularities, even at imaginary k, are important, and they tell us something physical and something very useful. Okay, and what is that? Well, suppose all I have access to is the hydrodynamic description of my theory. Okay, the late time description. So just, by definition, right, in the hydrodynamic limit, it's an effective theory. Everything is constructed as a series expansion in powers of k. Okay, in particular, yeah, the dispersion relation in the hydrodynamic limit, I should think of it as some series expansion in powers of k. And the fact hydrodynamics is an effective theory, what that means is eventually these series expansions break down, right? They have a finite radius of convergence where if you try and push them beyond that, they stop making any sense. Okay. And the important thing about these weird singularities, right, is that these are singularities in the dispersion relation omega of k. Okay, and it's these singularities that therefore are the closest such singularity to the origin is what controls the radius of convergence of this dispersion relation. So I think of omega of k as a power series, right? It's got a finite radius of convergence and it's set exactly where this singularity is. Okay, and this radius of convergence is, usually what people, how people characterize, where does hydrodynamics apply? You just compute the radius of convergence. That gives you a scale, right, beyond which, if you try and push hydrodynamics, you won't get anything sensible. Okay, and so this weird singularity here is exactly what's controlling the radius of convergence of hydrodynamics in this theory. Okay, and we can just read off exactly what it is in a high temperature limit. So it's given by pi times delta times T. Okay, and then there'll be corrections to this. Okay, so this weird singularity is telling us where does hydrodynamics break down. Okay, and perhaps even more importantly, it's telling us why hydrodynamics breaks down if you try and push it to too short distances, right? The reason is because you have other excitations, right? This guy here, which becomes important at this scale. And these guys are not accounted for by hydrodynamics. And so your effective theory breaks down when you try and go beyond it. Okay, so this is the other, and this is the other aspect of this kind of resummed two-point function I wanted to present. I mean, it looks at first like, oh no, this is bad. We've got something that doesn't make sense. But actually, it turns out to be good, right? It's actually telling us, it's showing us how this, if I try and push hydrodynamics to too early a time, it's showing us exactly, why it stops working, right? It's because we have extra degrees of freedom that aren't accounted for by this assumption of local thermal equilibrium. Okay, so this is what I wanted to say about, here's what I think the two-point function is, and here are some of its properties. What I want to go on to do now is to is to switch to talking about, to give you a bit of, evidence in terms of why should you believe that this guess is really the correct thing to do. And the first way I want to do that is to present some results from holographic theories, where we can really compute aspects of thermalization exactly, and to show you that at least the things we computed agree with the predictions that I just gave you. Okay, so the simplest type of holographic theory that has the properties we want is given by gravity in 3 dimensions coupled to a scalar field. Okay, so the scalar field captures the dynamics of that operator we're deforming our theory by. So we're going to allow the potential to be very general. So the leading term, a small field here, this is just the cosmological constant. The mass term, right, this just tells us the dimension of the Joule operator O. Okay, but beyond that, we're going to allow the potential to just be anything. Okay, so we're not just studying like a theory of gravity here, but a whole class of theories of gravity. Okay, there's 2 different types of classical solutions to this theory, which will interest us. So the first is basically what's dual to the conformal theory. So that is the solution where the scalar field is just 0. Okay, when that's the case, the metric just becomes the metric of the BTZ black hole. And since we're in 3 dimensions, right, there's not really a propagating graviton in this BTZ spacetime. The other class of solutions, which are more interesting for us, are those where we break conformal symmetry. So those are solutions to the Einstein equations where the scalar field is not 0, but it runs with the RG scale. And when the scalar field is not 0, that's going to back react on the metric. So the metric will no longer just be the BTZ metric. There's going to be some complicated thing that you have to construct numerically. But what's nice about this high temperature limit is in the high temperature limit, this back reaction of the scalar field onto the metric is small. Okay, so that's from the gravity point of view, what's nice about the high temperature limit is, okay, your space-time is not BTZ, but it's BTZ to a good approximation. Okay, so breaking conformal symmetry, just changes the sort of equilibrium, black hole solution. It also has another effect, which is much more important, which is that it couples the graviton to perturbations of the scalar field. Right? These things are no longer separate. They now couple to one another. And in 3 dimensions, scalar fields have a propagating degree of freedom. And since the graviton couples to that, what that means is when we break conformal symmetry, the graviton can now propagate. In particular, it can propagate behind the horizon. That leads to dissipation. And ultimately, that is why, that's the kind of gravity picture of why you need to break conformal symmetry to get this emergence of hydrodynamics. Right? Because that's what really gives you a graviton that can dissipate by getting absorbed by a horizon. Okay, so these are the kind of holographic theories that we're interested in. Now, in principle, what we could do is take these and try and just explicitly compute the 2-point function, right, in this limit and compare it to what I had before. So that is actually, a little bit complicated. So as our first pass, we did something a bit simpler, which is not to try and compute the whole 2-point function, but just to compute some simpler aspects of it, which are easy to access and which can be compared to the field theory result before. So let me explain the 2 things we calculated. So the first one is the viscosity. Okay, so there's a long history going back now of people studying fluids using holography, going under the name of fluid gravity correspondence. And thankfully for us, in 2009, Amos Yarom took this kind of theory and computed what is the viscosity of the fluid that emerges in the high temperature limit. Okay, and what he found is exactly this big complicated formula I wrote down before. Okay, so the viscosity agrees, right, with what we predict it would be. And we also did some numerical tests to check that, there's nothing funny happening in this computation, right? Really, if you do things exactly and then take the high temperature limit, you really get this answer. Okay, so the viscosity works. And the viscosity, right, remember, this is kind of the leading correction to the dispersion relation at small k. So really this is testing, does our guess really work at small frequencies and small wave numbers? Okay, that was the first thing. The second thing we tested it against is something called the locations of pole skipping points. Okay, so this takes a little bit of explaining, so please bear with me for a second. So first of all, what is a pole skipping point? So a pole skipping point is just a point in momentum space, complexified momentum space, where the retarded two-point function is undefined. Okay, and there's a nice intuitive picture of, how should I think about this, right? How does this happen? So at least in the kind of theories I'm talking about, we can think of the retarded two-point function in momentum space as being a ratio of, some numerator, which is a function of omega and k, divided by some denominator, which is a function of omega and k. Okay, this denominator will have zeros, which are like lines in omega k space, right? This is just like the dispersion relation of the pole, right? It'll have a, a line like this, and there'll be another one for another pole, another one for another pole. The numerator can also have zeros, which are lines in omega and k space, which you can think of as like the dispersion relation of the zeros of this two-point function. So a pole skipping point, I mean, the intuitive way to think about it are just points in momentum space where a pole and a zero intersect. Okay, and what's happening at these points is the numerator is zero, the denominator is zero, okay, and so the Green's function is just undefined, right? It's really just kind of infinitely multi-valued around this point. This value depends on how you approach the point. Okay, so this is some quite abstract feature of two-point functions. And the reason we focused on this is that in holographic theories, this abstract feature makes them very easy to identify. So in holographic theories, the points in momentum space, sorry, the pole skipping points are simply the points in Fourier space where the ingoing solution at the horizon is not unique. So normally to compute a retarded propagator in holography, we want to find the ingoing solution at the horizon. Okay, if that's not unique, right, then the retarded propagator is not unique. So that's how these are reflected in gravity theories. And what's very, convenient about that is to figure out when the ingoing solution to the black hole horizon is not unique. All we need to do is locally solve the gravitational equation of motion near the horizon. Right? Normally, to compute the full propagator, you got to solve the gravitational equations of motion everywhere in the space-time. Right? Just to figure out where something funny happens at the horizon, you just need to solve the equations of motion at the horizon. Okay, and that you can just do algebraically. Okay, so the upshot of what I'm saying here is we looked at these pole skipping points basically because these are a feature of the two-point function, which is very easy to calculate in a holographic theory. Okay, so in general in holographic theories, where are they located, right? What frequencies and wave numbers correspond to pole skipping points? Well, the frequencies where they happen are regular. So there's one at omega equals I2 pi t. There's one at 0. There's one at minus I2 pi t, minus I4 pi t, minus I6 pi t, etc., etc. And at certain values of the wave number. Now, the value of the wave number is usually just some complicated expression that depends on exactly what theory you're talking about. But the exception to that is the n equals 0 mode, so the one in the upper half frequency plane. So in general, in holographic theories, the location of the pole skipping point in the upper half frequency plane, the wave number, is directly related to the butterfly velocity, right? Which is a kind of another observable that characterizes some aspect of thermalization. So I'm not going to go into exactly what the butterfly velocity is, but the point here is just this particular pole skipping point, right, has a direct physical meaning in terms of thermalization. It tells us the butterfly velocity. The other ones don't. So what we can do is go to our guess of the resummed correlator and just read off, where are the pole skipping points? Or more accurately, what we're going to do is read off where do the poles of this two-point function pass through these special frequencies. Okay, so remember, pole skipping point is where a pole and a zero intersect, and so we need a pole to pass through this frequency. Now, in fact, we don't need to look at all the values of n because only n equals 0, n equals 1, and n equals 2 have a 0 in the right place. So we're just going to look at the poles, where the poles pass through this expression for n equals 0, n equals 1, n equals 2. Okay, there's one trivial one, which is n equals 1. Okay, so our pole, we always have a pole at 0 frequency and 0 wave number, right? There's nothing magical there. That's just guaranteed by hydrodynamics. So it's not really telling us anything interesting. But the other two are telling us something interesting. So we can read off, right? Where would the pole skipping point be at n equals 0? And it's given by this complicated function. And where would the pole skipping point be at n equals 2? Okay, and it's given by this slightly different complicated function. Okay, and the important thing to note about these, right, is these pole skipping points are related, are located at wave numbers that are basically order temperature. Okay, so this kind of prediction here, if I scroll back to my picture, right, is testing, is there really a pole, right, where I say there is here, right? We're way outside the range of radius of convergence of hydrodynamics, right? We're not testing hydrodynamics here. We're testing, is our guess really correct? Some intermediate point between early times and late times. Okay, and this is what our guess tells us where the pole skipping point should be. So now we can go to our holographic theory. As I said, these have infinitely many pole skipping points. And what we find is 3 of them agree exactly with these predictions, i.e. there's a pole skipping point here, there's a pole skipping point here, and there's a pole skipping point here. Okay, so this is, to me, kind of very convincing evidence that this guess really is correct, right? I don't think there's a way you could get the right answer here if your 2-point function was wrong. Okay, and what that means, since one of these pole skipping points also tells us the butterfly velocity, is that this naive resummation is also giving us the correct butterfly velocity. Okay, so this butterfly velocity was computed in other ways. Sorry, this should say 2024, and by these authors, and it agrees with what you would read off from this guessed resummation. So this is 3 of them. As I said, there's infinitely many of them, and in holography, we don't have to make some near-lightcone approximation, but we can really just compute exactly where they all are. And we find, indeed, none of the others are anywhere near the light cone, right? That's why we don't see them in this field theory picture. And furthermore, the wave numbers of all the other ones are not universal, i.e. they don't just depend on the scaling dimension delta. They depend on, more complicated details of the scalar potential. And so what I want to kind of emphasize, so this is good. I'd say this is, kind of, to me, sort of compelling evidence that holographic theories, this is really the correct answer. And maybe something I want to emphasize here is the fact that I'm saying that this correlator is universal, right? That's not obvious, right? I'm saying in this particular limit, the correlator is universal, right? And this is a way to see that it's not obvious. It's just, if you really compute the 2-point function holography, all kind of aspects of it depend on complicated details of the scalar potential, right? It's really just in this near-lightcone high temperature limit that everything becomes universal. Okay. So this is this kind of section on holographic theories. And the upshot of this is they agree with the result. So in the last couple of minutes now, let me go back and try and give you a picture of how thermalization is happening and how we can try and prove this resummed 2-point function, even outside the regime of holographic theories. So let's go back to conformal perturbation theory, but this time work in real space rather than momentum space. Okay, so this is the momentum space. This is the first correction in momentum space. The important term, as I emphasized, is this one on the second line. And conceptually, how we should think about this is as the product of 3 2-point functions, right? One of them is just the scalar 2-point function in the CFT. And then we've got 2 copies of omega plus k divided by omega minus k. Right, which schematically, right, is just 2 copies of the stress tensor 2-point function near the light cone in the CFT. Okay, so to get the real space correction, we can Fourier transform this. Okay, and so what's happening when we Fourier transform it is, so we're computing a 2-point function between insert an operator here and an operator here. Okay, and we've got a convolution here. So first of all, our stress tensor propagates, right, like a CFT stress tensor just along the light cone, right, for some time. Then we insert, a 2-point function of O, and then we get some propagation, right, with this propagator here. Okay, and then we have a final propagation by the stress tensor 2-point function, again, along the light cone. Okay, so we can do this integral exactly, but before presenting the exact result, let me explain the sort of important features of it. Right, what can we expect to get from this correction? So the first thing is that this correction we expect is going to cause spreading of the two-point function up to some thermal distance inside the light cone. Okay, and the reason is simply that in the thermal state, right, the two-point function of O, right, is exponentially suppressed, right, if we're more than a thermal distance, right, for separation of more than a thermal distance. Right, so this is going to be non-zero for some kind of thermal distance like that. So this is CFT just goes along the light cone. This correction is going to cause it to spread inside. That's the first thing. The second thing is this correction is going to not die out at late times. Okay, and not only is it not going to die out at late times, we expect it's going to grow at late times. So the reason it doesn't die out at late times, right, is the stress tensor propagator, since it's chiral, okay, just propagates freely along this direction, right, even in the thermal state. Right? Normally, in a thermal state, everything decays exponentially, okay, because the stress tensor doesn't depend on one of the coordinates, it doesn't decay even in a thermal state along this direction. Okay, so that's why it becomes important, it stays important at late times. And the reason, in fact, it grows at late times is, it's basically the same thing. We're inserting this two-point function, right? We're integrating over where we insert it. Okay, and since this propagator and that propagator, right, are independent of this direction, right, we can insert this pair of O's anywhere we like along this light cone. Okay, and it's not going to change the answer. And so when we integrate over the insertion positions, we're going to integrate over this distance. Right? It's going to integrate over time. That's kind of physically what's happening here. And if you just explicitly do this integral, you find basically what I said. So the important term is this one here. So you get a result which grows linearly at late times. Okay, and so this is like the position space picture, if you like, of how conformal perturbation theory is breaking down at late times. So this correction is suppressed by lambda bar squared, right? But it's enhanced by a factor of the time. Okay, and if you compare this to the leading order result, you see indeed the sort of ratio of them is given by lambda bar squared times time. And so even when lambda bar is very, very small, at late enough times, conformal perturbation theory breaks down. Okay, and it breaks down because of this free propagation of stress tensors, even in the thermal state. Okay, so this is the kind of this suggests, let's say this is just the first correction, but it suggests conformal perturbation theory is going to break down near the light cone at this time scale here. Okay, what about at higher orders? So at higher orders, I don't have any explicit computations to show you, but what I want to explain is at least, so for what I'm saying to make sense, it must be that higher and higher orders, we just keep getting this effect worse and worse and worse, right? Otherwise, we don't really lose control. So what I want to give you is a kind of cartoon of what are the effects at higher order in conformal perturbation theory, which are going to lead to these worse and worse divergences and essentially cause thermalization. So if we're at order 2n in conformal perturbation theory, that means the thing we want to compute is an integrated two-point function where we have two stress tensors, and then 2n scalars. Okay, and we want to figure out what is the contribution from this expression, which is going to, be non-zero and in fact grow with time. So the first thing is we better insert these O's in pairs. Again, as I said before, if they're more than a thermal distance apart, they're going to be exponentially suppressed. So we need to insert them in pairs. Right, that's what I'm doing here.
So may I ask you a question on this? So
Sure.
Even at zero temperature, usually higher order conformal perturbation theory is not scheme independent. So I think I believe that your first order is scheme independent, but the higher order most probably are not, right?
Yeah, probably not. So we were not able to compute, any of these explicitly. So I can't, I don't know is the answer. But I'm going to give you a kind of hand-waving cartoon of if you could do the calculation, I think here are the important terms to calculate. If you see what I
Okay, I see. Thank you.
Yeah, so we've got pairs of O's, and what we're going to want to do is fuse them together, okay, and pick out, right, what are the operators that these fuse into that are going to cause, right, that are going to give us the important effects. Okay, and the point here is just the same as it was at first order in conformal perturbation theory. Okay, to have a big effect at late times, we want to fuse these guys into things which can propagate freely in this direction. Okay, otherwise they're just going to exponentially decay, right, in the thermal state. And so that means we need the important contributions are going to come when we fuse these guys into chiral operators, i.e. the stress tensor and its descendants, right, assuming there are no other conserved currents. Okay, and if we do that, again, we'll have the same situation as before, right? We're inserting these pairs of O's, but really we can freely slide them up and down, right, without changing the value of the integral. And since we're integrating over their position, we're going to get an enhancement, which is, you know, right, the insertion time to the power of n. Yeah, so I mean that's the basic idea, right? That's what's causing conformal perturbation theory to break down, is this exchange of stress tensors, which even in the thermal state is unsuppressed. Okay, and really to do this properly, of course, you'd have to evaluate some horrendous, you know, 2n plus 2 point function of stress tensors, and what we hope or expect is that this is where the large C limit comes in, right? At large C, this is going to factorize in momentum space into just products of 2-point functions, right? This is just a 2-point function of the stress tensor. This is just a 2-point function of the scalar. And it's going to reproduce every order in conformal perturbation theory, right? Exactly the thing that we need it to so that we can resum it in the way that we think we should. Okay, so I'm already a couple of minutes over time, so let me just give you a quick summary. So the main takeaways are that 1 plus 1D QFTs at high temperatures thermalize slowly over this time scale. And the way they thermalize from the microscopic point of view is this exchange of stress tensors near the light cone. Okay, and to get the correct late time physics, which would be hydrodynamics, right, we need to resum these effects. Okay. That's the first takeaway. The second one is I'm proposing that this thermal 2-point function is universal in the high temperature near light cone limit. And I have some explicit expression for it. And using this, you know, it gives us universal results for all kinds of interesting non-equilibrium quantities, transport coefficients, butterfly, velocity, radius of convergence of hydrodynamics, etc., etc. And at least the ones we checked of these agree with explicit computations and holographic theories. Okay, and I think, I mean, from my point of view, there's still loads of very interesting questions here. So perhaps the main one is, can we really do what I outlined before? Can we really derive hydrodynamics by resumming these effects in conformal perturbation theory, right? If this is really the answer, okay, and at least in holographic theories, I think it is, right? This should be a doable computation. And if we can do it, you know, it should help perhaps shed a bit of light on exactly what are the conditions the CFD has to satisfy that this is correct, right? It seems to be true in holographic theories. Does it really rely on holography? My instinct is no. It seems to, you know, that's my instinct, but of course I can't prove it to you. So are there any other conditions on the CFT besides what we've assumed? And there's lots of other interesting directions. So one of which is what happens away from the light cone. So we also have a proposal for what things look like away from the light cone. But we don't have any evidence for that, so I didn't want to talk about it. What about higher point functions of the stress tensor, right? Can we similarly get very nice universal expressions for higher point functions? There's a very similar story to what I've described here when I'm talking about the high temperature limit that applies in the low temperature limit. So there we'd have an IR CFT deformed by some irrelevant operator. There's some subtleties there regarding DT bar deformations and so on that it would be nice to resolve. What happens when there are additional global symmetries? So for example, say I have a conserved U1 current as well, right? Then hydrodynamics doesn't just take place near the light cone, there's more complicated things happening, right? Can I make any progress understanding what happens there? Are there any lessons for thermalization in higher dimensions? And finally, this is probably the most difficult one, what happens away from the large C limit? Okay, but thank you very much for your attention. I'm going to stop there and I'll be happy to answer any questions.